Greetings, fellow space explorers. Today, we're diving headfirst into a realm where the familiar laws of physics get a serious makeover. Buckle up as we venture into the captivating world of antimatter. Imagine a substance so bizarre, so profoundly different from anything we encounter daily, that it seems ripped straight from the pages of science fiction. This isn't just the stuff of imaginative tales. Antimatter is a real phenomenon, and it holds the potential to rewrite our understanding of the cosmos. Our journey will take us from the subatomic realm, where particles dance and collide with their antimatter counterparts, to the grand stage of the universe itself. Prepare to have your mind stretched, your curiosity ignited, and your imagination sent into overdrive. So, without further ado, let's embark on this extraordinary adventure into the heart of antimatter. Antimatter, in its simplest form, is the polar opposite of matter. Imagine everything you know about the physical world, the atoms that make up your body, the air you breathe, the ground beneath your feet, and then picture it with its charges reversed. Instead of positively charged protons nestled within the atom's nucleus, antimatter boasts negatively charged antiprotons. And in the realm of antimatter, the negatively charged electrons orbiting the nucleus are replaced by their positively charged counterparts, known as positrons. This asymmetry, this apparent imbalance in the cosmic scales, is one of the most profound puzzles facing modern physics. To truly grasp the enigma of antimatter, we must first delve into the fundamental building blocks of our universe, particles. These tiny specks of energy and matter form the very fabric of reality, and their interactions govern everything from the formation of stars to the functioning of our own bodies. But for every particle that makes up the world we know, there exists an antiparticle, its mirror image in the antimatter realm. Take, for example, the humble electron, a negatively charged particle zipping around the nucleus of every atom. Its antimatter counterpart, the positron, possesses the same mass but carries a positive charge. The meeting of matter and antimatter results in a spectacular release of energy known as annihilation. Now, if the universe truly began with a perfectly balanced cocktail of matter and antimatter, as many theories suggest, we'd expect to see evidence of their ongoing annihilation all around us. Yet, we find ourselves living in a universe seemingly dominated by matter. This glaring asymmetry, this cosmic imbalance between matter and antimatter, is one of the most perplexing mysteries in modern physics. One intriguing possibility is that the early universe in its infancy played host to processes that subtly favored the production of matter over antimatter. But unraveling this cosmic puzzle requires us to peer deep into the heart of the Big Bang, the ultimate frontier of our understanding. Our journey into the heart of antimatter begins not in the depths of space, but in the realm of human imagination. For centuries, philosophers and scientists have pondered the fundamental nature of reality, seeking the building blocks of our universe. But it wasn't until the early 20th century that the concept of antimatter began to take shape, emerging from the swirling mists of theoretical physics. The quest for antimatter wasn't driven by a desire to find a mirror image of our world, but rather by a deep-seated need to understand the fundamental laws governing the universe. Physicists, armed with new theories and emboldened by a spirit of discovery, set out to explore the uncharted territories of the subatomic realm. In 1928, a young British physicist named Paul Dirac set the stage for one of the most profound discoveries in the history of science. Dirac, known for his brilliance and eccentricities, was wrestling with the equations that sought to unify quantum mechanics and Einstein's theory of special relativity. Dirac's equations, elegant and deceptively simple, described the behavior of electrons, those tiny negatively charged particles that buzz around the nucleus of every atom. But his equations held a surprising twist. They predicted the existence of another particle, one with the same mass as the electron but carrying a positive charge. Dirac's bold prediction sparked a flurry of excitement and skepticism among physicists. The idea of antimatter, while mathematically sound, seemed almost too bizarre to be true. To confirm its existence, scientists needed concrete evidence, a smoking gun from the subatomic realm. And they found their hunting ground in the most unexpected of places: cosmic rays. Cosmic rays, those high-energy particles bombarding Earth from the depths of space, provided a natural laboratory to study the fundamental building blocks of matter. In 1932, American physicist Carl Anderson made a discovery that would change the course of scientific history. While studying cosmic rays using a cloud chamber, Anderson observed a peculiar track, one that defied conventional explanation. This track, curved by a magnetic field, hinted at the presence of a positively charged particle with the same mass as an electron. This positively charged particle, dubbed the positron, behaved exactly as Dirac's theory had predicted, confirming the existence of antimatter. The discovery of the positron sent shockwaves through the scientific community. The discovery of the positron was just the tip of the iceberg. As physicists delved deeper into the subatomic realm, they uncovered a treasure trove of antimatter particles, each one a mirror image of its matter counterpart. For every proton, there existed an antiproton; for every neutron, an antineutron. The universe, it seemed, was built upon a fundamental symmetry, a delicate balance between matter and antimatter. When worlds collide, the explosive power of annihilation. We've talked about antimatter being the mirror image of matter, with opposite charges but equal mass. But what happens when these two cosmic opposites meet? Get ready for the ultimate showdown, folks, because it's not just a matter of shaking hands and going their separate ways. When matter and antimatter collide, they annihilate each other in a spectacular release of pure energy. Imagine the most powerful explosion you can fathom, then multiply it by, well, a lot. Annihilation unlocks that energy, converting the entire mass of both particles into pure energy. This isn't just theoretical physics, folks. Scientists have observed annihilation events in laboratories, witnessing firsthand the incredible energy released when matter and antimatter collide. The sheer energy unleashed during annihilation has sparked the imagination of scientists and science fiction writers alike. Just imagine a fuel source so potent, so efficient that it could power starships to distant galaxies or solve our energy woes here on Earth. Antimatter, with its unparalleled energy density, holds the key to unlocking the ultimate power source. A single gram of antimatter, annihilating with an equal amount of matter, could release the energy equivalent of a nuclear bomb. Producing and storing significant amounts of antimatter is a challenge that continues to vex scientists. But the potential rewards are simply too great to ignore. Here's where things get really interesting, and by interesting I mean mind-bogglingly puzzling. If the Big Bang created equal amounts of matter and antimatter as many theories suggest, then the universe should be a much quieter place. In fact, it shouldn't exist at all. All that matter and antimatter should have annihilated each other shortly after the Big Bang, leaving behind nothing but a sea of energy. But here we are, in a universe teeming with galaxies, stars, planets, and even life itself. This is the crux of the matter-antimatter asymmetry problem. Why is there so much more matter than antimatter in the observable universe? Scientists aren't just sitting around pondering the mysteries of antimatter, they're actively searching for answers, using some of the most sophisticated tools ever devised. Particle accelerators like the Large Hadron Collider at CERN smash protons together at near-light speeds, recreating the extreme conditions of the early universe. These collisions produce a shower of particles, including, you guessed it, antimatter. By studying these antimatter particles, physicists hope to unlock the secrets of their creation and understand why they're so rare in the universe today. The quest for antimatter's origins is a cosmic detective story, and each new experiment, each observation, brings us closer to understanding this fundamental aspect of our universe. Antimatter has captured the imagination of science fiction writers for decades, fueling stories of interstellar travel, powerful weapons, and even alternate universes. From Star Trek's warp drive to the angels and demons, antimatter has become a staple of science fiction, often portrayed as a source of both wonder and destruction. But while the fictional portrayals of antimatter can be entertaining, it's important to separate science fact from science fiction. While antimatter does hold immense energy potential, we're a long way from using it to power starships or create doomsday devices. And while we might not have warp drive just yet, antimatter is already being used in medical imaging techniques like PET scans, demonstrating its real-world potential beyond the realm of science fiction. Alright, space cadets, let's bring antimatter down to Earth for a moment, literally. While the idea of antimatter might conjure images of futuristic starships and mind-bending physics, it's already playing a crucial role in a field much closer to home medicine. You see, antimatter isn't just a theoretical curiosity, it's a powerful tool that's helping us understand and treat diseases in ways never before imagined. One of the most remarkable applications of antimatter is in positron emission tomography, better known as PET scans. This imaging technique allows doctors to peer inside the human body with incredible precision, revealing the intricate workings of our organs and tissues at a molecular level. So how does it work? Well, it all starts with a small amount of a radioactive tracer, a substance that emits positrons, those antimatter counterparts of electrons we talked about earlier. This tracer is injected into the patient's body, where it's absorbed by specific organs or tissues, depending on the type of tracer used. As the tracer decays, it releases positrons, which then encounter their matter counterparts, electrons, within the body. Remember what happens when matter and antimatter collide? That's right, annihilation. And in this case, the annihilation process produces gamma rays, a type of high-energy light that can be detected by the PET scanner. Let's talk about something that excites engineers and science fiction fans alike: energy. In a world grappling with climate change, the search for clean energy is critical. Antimatter might hold the key to the ultimate power source. A single gram of antimatter could release energy equivalent to a nuclear bomb. Imagine a future with no fossil fuels and no emissions. But harnessing this power is a monumental challenge. The potential rewards are too great to ignore. Antimatter could unlock interstellar travel, opening up the cosmos. Speaking of interstellar travel, let's indulge our inner space explorers. Imagine a future where humanity has ventured beyond Earth, establishing outposts on Mars, mining asteroids, and maybe even shaking hands, or tentacles, with extraterrestrial life. Antimatter could help us achieve this. Traditional rockets are too inefficient for interstellar journeys. That's where antimatter comes in. Its energy density makes it ideal for interstellar travel. Such a spacecraft could achieve speeds approaching the speed of light, reducing travel times to the nearest stars from thousands of years to decades. Let's come back to present-day science and engineering. Harnessing antimatter's power is no walk in the park. It's like juggling chainsaws on a unicycle over a volcano. Production is a major challenge. Particle accelerators are our best bet for creating antimatter, but they produce just a handful of atoms at a time. Storing antimatter is another headache. Antimatter annihilates matter on contact. We need to isolate it from regular matter. Scientists are exploring magnetic traps and laser cooling techniques. Let's talk money, folks. Research and development require significant financial investment. Producing even a single gram of antimatter costs trillions of dollars. That's right, trillions with a T. The entire global economy is measured in the tens of trillions. Until we find cost-effective ways to produce and store it, antimatter remains science fiction. But history shows technological advancements can reduce costs dramatically. Remember how expensive computers were? Now, we carry more computing power in our pockets. The same could apply to antimatter. Alright, space enthusiasts, buckle up because we're about to take a trip to the cutting edge of science. Forget about time machines and teleportation devices, we're talking about real-life machines that can unlock the secrets of the universe particle accelerators. Now, when it comes to particle accelerators, CERN, the European Organization for Nuclear Research, is like the rock star of the science world. This sprawling complex, located near Geneva, Switzerland, is home to some of the most sophisticated scientific instruments ever built, including the world-famous Large Hadron Collider, or LHC. Imagine a giant underground racetrack, stretching for miles, where protons, those tiny particles found in the heart of atoms, are accelerated to near-light speeds and then smashed together in spectacular collisions. That's the LHC in a nutshell. It's like a giant microscope, allowing us to peer into the subatomic realm and study the fundamental building blocks of matter. But here's the really cool part. These high-energy collisions don't just reveal the secrets of existing particles, they can actually create new ones, including, you guessed it, antimatter. So how do these particle accelerators actually create antimatter? Well, it all comes down to Einstein's famous equation, E equals mc squared, which tells us that energy and mass are two sides of the same coin. When those protons collide inside the LHC at near light speeds, they pack an incredible amount of energy. This energy is so intense that it can actually convert into mass, creating a shower of new particles, some of which are antimatter. It's like a cosmic game of billiards where the energy from the collision creates new balls, some of which are made of antimatter. Now, before you get too excited about mass-producing antimatter for all sorts of futuristic applications, there's a catch, and it's a big one. These collisions produce minuscule amounts of antimatter, literally just a handful of antiprotons or positrons at a time. Think about it this way. If you were trying to collect a teaspoon of antimatter, it would take you longer than the age of the universe using current technology. Yeah, it's that rare. But hey, scientists are a persistent bunch and they're constantly developing new techniques to improve the efficiency of antimatter production. We've talked about the incredible energy released during matter-antimatter annihilation, but here's a mind-bending thought. That very process works against us when we try to create antimatter. You see, as soon as an antimatter particle is created, it's surrounded by a sea of matter like a lone wolf venturing into a pack of hungry rivals. This means that our newly formed antimatter particle is in constant danger of being annihilated before we can even say, "Beam me up, Scotty." It's like trying to catch a snowflake on your tongue in the middle of a blizzard. To make matters even more challenging, antimatter is electrically charged, which means it interacts strongly with electromagnetic fields. This makes it incredibly difficult to contain and control. It's like trying to wrangle a bunch of hyperactive fireflies in a thunderstorm. Despite these formidable challenges, scientists have made remarkable progress in trapping and studying antimatter, and while we're a long way from mass-producing it, each new discovery brings us closer to unlocking the full potential of this enigmatic substance. Section 4, Trapping the Elusive, the Art of Storing Antimatter. Alright, let's say we've managed to create a few precious antimatter particles. Now, how do we keep them from instantly annihilating with regular matter? It's like trying to store nitroglycerin in a fireworks factory, except a million times more delicate. This is where the ingenuity of scientists really shines. They've devised ingenious traps, like the penning trap, which use a combination of electric and magnetic fields to suspend charged antimatter particles like antiprotons in a near-perfect vacuum. Imagine a tiny invisible force field, carefully crafted to keep those antimatter particles from touching the walls of their container, which of course are made of regular matter. But even with these sophisticated traps, storing antimatter for long periods is a constant battle against the odds. The slightest imperfection in the magnetic field, the tiniest vibration, can spell disaster, leading to a catastrophic release of energy. It's like trying to balance a bowling ball on the tip of a needle during an earthquake. But hey, challenges are what drive scientific progress, and the quest to tame antimatter is no exception. Section 5, The Future of Antimatter, From Science Fiction to Scientific Reality. We've journeyed from giant particle accelerators to trapping individual antimatter particles. What does the future hold for this enigmatic substance? Antimatter is already making its mark in medical imaging. PET scans rely on positrons to produce detailed images of the human body. As our understanding grows, so will its applications. Imagine antimatter powering spacecraft on interplanetary missions or providing clean, efficient energy. These might sound like science fiction, but the line between science fiction and reality is constantly being blurred. Section 1. Antimatter on the silver screen. Hollywood's take on the cosmic twin. Let's face it, folks, antimatter has a certain allure that Hollywood just can't resist. It's mysterious, it's powerful, and it sounds downright cool. So it's no surprise that antimatter has made its way into countless science fiction films and TV shows, often serving as a plot device for everything from interstellar travel to apocalyptic weapons. Remember the warp drive in Star Trek, allowing the Starship Enterprise to zip across the galaxy faster than a speeding photon? Yep, you guessed it, antimatter was the fuel source that made those interstellar joyrides possible. And who could forget the terrifying antimatter bomb in Angels and Demons, threatening to wipe out Vatican City in a blaze of cosmic energy? Hollywood loves to play with antimatter, often exaggerating its properties for dramatic effect. But hey, who can blame them? Antimatter is inherently cool, and it makes for some pretty spectacular visuals on the big screen. While those cinematic depictions of antimatter might make for thrilling entertainment, it's important to remember that Hollywood takes some, shall we say, creative liberties when it comes to scientific accuracy. Don't get me wrong, I love a good science fiction movie as much as the next space enthusiast, but it's crucial to separate the science fact from the science fiction. Take warp drive, for example. The idea of bending space-time to achieve faster-than-light travel is a fascinating concept rooted in theoretical physics. However, the amount of antimatter required to power such a device would be astronomical, literally. We're talking about more antimatter than we could realistically produce in a million years using current technology. And as for those city-destroying antimatter bombs, while the energy released during matter-antimatter annihilation is indeed formidable, creating a weaponized device capable of such destruction faces immense technical hurdles. Remember those challenges we talked about with production, storage, and containment? Yeah, those don't magically disappear just because it's a Hollywood movie. So if we strip away the Hollywood hype, what are we left with? Is antimatter just a figment of science fiction, or does it hold real-world potential beyond the silver screen? The answer, my friends, is that antimatter is a very real phenomenon with tangible applications that are already impacting our lives. Take PET scans, for example. This medical imaging technique, which relies on the annihilation of positrons with electrons within the body, is used every day to diagnose and treat diseases from cancer to heart disease. And while we're not building warp drives or antimatter bombs anytime soon, the study of antimatter continues to push the boundaries of our understanding of the universe. From exploring the fundamental nature of matter and antimatter to unlocking the secrets of the Big Bang, antimatter research is a journey of discovery with profound implications for our understanding of the cosmos. As we conclude our exploration of antimatter, it's clear that this enigmatic substance continues to captivate our imaginations and challenge our understanding of the universe. From its dramatic discovery to its mind-bending properties, antimatter has earned its place as one of the most fascinating and perplexing phenomena in the cosmos. While we've made significant strides in unlocking the secrets of antimatter, many mysteries remain. Why is there so little antimatter in the observable universe? Could there be hidden pockets of antimatter out there, perhaps even entire anti-stars and anti-galaxies? And could antimatter hold the key to solving some of the most fundamental questions about the universe's origins and evolution? These are questions that will continue to drive scientific inquiry for generations to come. The journey into the heart of antimatter is far from over. It's a journey fueled by curiosity, driven by innovation, and ultimately, a testament to the boundless capacity of the human mind to explore and understand the universe we inhabit. From the tiniest particles to the grand expanse of the cosmos, antimatter has taken us on a mind-bending journey. We've delved into the heart of atoms, witnessed the explosive power of annihilation, and pondered the fate of the universe's missing antimatter. It's a story filled with scientific breakthroughs, enduring mysteries, and the tantalizing promise of future discoveries. While antimatter might seem like something straight out of science fiction, its existence is a testament to the elegant and often counterintuitive nature of the universe we inhabit. It reminds us that the cosmos is full of surprises, waiting to be uncovered by those who dare to ask the big questions. As we continue to explore the universe and unravel its secrets, antimatter will undoubtedly play a pivotal role. It challenges our assumptions, pushes the boundaries of our knowledge, and beckons us to venture further into the unknown. So the next time you gaze up at the night sky, remember that for every twinkling star, for every distant galaxy, there might just be a mirror image out there, a realm of antimatter forever bound to our own by the fundamental laws of physics. And who knows, perhaps someday we'll unlock the secrets of this cosmic twin and unlock a new era of scientific understanding.